All right, we're going to be changing pace a bit more. We've spent a lot of time thinking about how the electrons surround atoms, what sort of bonds they create, how they create arrangements of the atoms in space. So we're going to talk a lot more about how those arrangements of atoms to form molecules have consequences in the chemical properties of the molecules. So let's go over some of the objectives for this lecture segment. We are going to talking about describing the main types of intermolecular interactions, the interactions between molecules, the reasons for these interactions and how strong they are, recognize which intermolecular interactions are present given a molecular structure, and be able to predict rankings of physical properties based on strengths of interactions of the molecules. So we're going to back up a little bit and say, all these, how do molecules arrange themselves in space? And so we know that there's several different phases that we commonly observe. One is gas. We know about the gas, it's fluid. It flows around, it's flowing around my arms now, and compressible. We spent a lot of time looking at, PV equals nRT. Its structure is the gas molecules are random, fluctuating, and very dilute. You don't have very many gas molecules per volume of space. And the molecules are in motion, and we know they have very weak interactions. In fact, we can model them pretty well by saying they have no interactions whatsoever. The van der Waals gas model starts to bring into the fact that they might have some weak interactions attracting each other. Okay, so liquids are different. They're fluids. You can pour a liquid around very easily, but it's mostly incompressible. If you've ever tried to like compress a gallon of water or something, that does not give very easily compared to air. They're still random and fluctuating, but they're dense. The molecules are in motion, and you have relatively strong interactions between them. Solids are generally rigid or semi-rigid, generally incompressible. And their structures, rather than it might still be random. Sometimes it's random, sometimes it's ordered, but it's persistent, and they're quite dense. About as dense as fluids are. The molecules are fixed in position, and they're fixed in position by the strong interactions between them. And so that's really actually the major differences we see between different phases are the strength of the interactions between them. Gases, at a given temperature, gases will have relatively weak strength. Liquids will have larger strength, and solids will have very strong interactions between the molecules. There's a few other factors that are important, like the shape of the molecule and how well they can pack, but generally it just has to do with the intermolecular strength. If you have strong intermolecular interactions, then you'll form a liquid or a solid at a much lower temperature. They'll still be lowered at a separate temperature because the kinetic energy of rattling around cannot overcome the potential energy of those strong interactions in between the molecules. So in order to understand the phases of matter, we really need to understand the interactions that are causing those changes in phases. So primarily, these different phases, these different behaviors are caused by attractive forces between molecules because the ideal behavior in gases and allow liquid and solid phases to exist at relatively high temperatures. Okay, so that's sort of the phases we get. What are the properties that we observe because of these intermolecular motions? How do we macroscopically observe these interactions that have to do with how the molecules are interacting at the nanometer scale? So So stronger intermolecular forces make it more difficult to pull molecules apart in condensed phases, i.e. liquids or solids. And if they're harder to pull apart, then, for example, liquids have a higher boiling point. It takes more kinetic energy to rip molecules out of the liquid into the gas phase. They have a larger enthalpy of vaporization. You need at that higher boiling point, that has a higher boiling point because you need to pump more energy in to pull each individual molecule away, and that's the enthalpy of phase change. A greater surface tension, talk a little more about that as well, and a greater viscosity. That has to do with the thickness. Like maple syrup has a high viscosity, water does not have a particularly high viscosity. But if you look at something like, paint thinner or something, those have even lower viscosities than water. For solids, a higher melting point, similarly to the boiling point, you need if there's strong intermolecular forces, you'll have a higher melting point and a larger enthalpy of fusion, the energy required to get between the solid and liquid phases. Okay, so those are that's important we understand intermolecular forces so we can predict these various properties of solids and liquids. So surface tension, let me just explain why surface tension relates to stronger intermolecular interactions. So strong intermolecular interactions mean large surface tension. Why is that? Well, if you imagine molecules at a surface, the surface molecule has to be interacting with the surface. So it only interacts with a few neighbors. Whereas you have a molecule in the interior, in the bulk, it gets to interact with a lot of neighbors. So if it wants to be with its neighbors, then the surface molecule really doesn't want to be there. You want to have, the fluid will arrange itself so as few molecules as possible are in contact with the surface. And that's what surface tension is. It's an attempt to minimize the surface area. So strong intermolecular interactions, large surface tension, rather than spreading out, the liquid beads up. Remember, if you look at beads on a greasy surface, you can see the beads are very curved because they're trying to take a shape that is as spherical as possible, that is as little interaction with the surface as possible. Okay, so stronger, and for viscosity, remember viscosity has to do with the thickness of a fluid, how hard it is to stir. Stronger intermolecular interactions will be more viscosity. It's more gluey. They like to stick to each other more. It's harder to move them around. There are a few other factors that affect viscosity, like shapes that can snag each other. Like nice round shapes tend to roll past each other. Those will generally have lower viscosity, while as larger, sticky or stringy shapes, you have longer polymers particularly, or things we'll talk about more like hydrogen bonds like to stick to each other, those will generally have a larger viscosities as well. So you have both the strength of the interactions and how the shape of the molecules, how tangled up they get in each other. A temperature overcomes both effects. So at higher temperatures, everything becomes less viscous because there's enough bouncing around to either bounce away from the intermolecular interactions or to go around the stringinesses.